Okay, so let's say we have, this is our, and then in Europe, it would be 50 hertz, you know. So then we could change this one, you're changing the peak voltage. So you could go 100 millivolts, 1 kilovolt. So you're changing the amplitude of the voltage. So if we wanted to mimic the power output of the America, what would we put here for what would we put for the peak voltage? We would put 120 root 2, right? Whatever that was. What did we get a minute ago? So this is kind of where things get practical, right? When you're gonna do, when you're mimicking things, you really gotta understand what to put, right? So remember, we said in America the root mean square voltage is 120, but the peak voltage or the maximum voltage is 120 root 2, which is 169. So in order to mimic an outlet source, we would put this one, we would put 170 volts, 170. You see that? Then the voltage would go up to 170 and down to negative 170. Up to 170, then down to negative 170, you see. So now we could put a resistor in the circuit. Let's see, where is our resistor? You could put any value to the resistor. Let's say 300 ohms. Then we could take an inductor. Let's say 20 millihenries. Okay, then close the circuit. Okay. So what do we expect? So now if I take the voltmeter, this is, oops, something burned. Beyond Labs does that. If there's too much current and the thing can't take it, it's very realistic. It actually burns. Which one burned? Oh, the resistor burned. Oh, maybe I have too much power, 170 volts. Let's make it, well, let's make it down. We could scale it down to 17 volts. Then they'll mimic our power outlet, but it won't be as big. So the root mean square voltage will still be 12 volts, you know. Okay, so then I have to put another one here because this one's already burned. Put this one. Okay, so now if I take the multimeter and go across this, the DMM means digital multimeter. Okay, now this one I have to put, you see, it's going crazy because I don't have it on DC, I don't have it on AC volts. So it's taking the literal instantaneous voltage and just going crazy. So you go like this, this is the root mean square voltage. You see the root mean square voltage is 12. So we should be able to calculate all these and get percent errors essentially. You see, it's 12 volts. So let's write that experimentally. So we have 300 ohms. It came out what? 0.302 volts. We go to AC current. Okay, then that's going to give us the root mean square current in the circuit. What is that? 0.04 amps. 0.040 amps. The information I've got so far. I've got the resistor is 300. This is 20 millihenries. The frequency of the source is 60. The maximum of the source is 17, but this is what matters more. 12. This one, experimental root mean square of the resistor is 12.01. Inductor is 0.302. This one is 0.04. Okay, now let's calculate the period of one cycle. Period, what's the connection between period and frequency? Period is 1 over frequency, right? 1 divided by 60. So 0.016666. So if we use the frequency that is for America, the period of the cycle is this many seconds, which means how many milliseconds? 16.66 milliseconds. So in order for us to catch on the oscilloscope, let's say the oscilloscope is like this. In order for us to catch what's going on to the source voltage or to the resistor voltage for a whole period, right? We would have to capture like around from one end to the other, around 20 milliseconds at least. 20 milliseconds of the action. So now we could check the total voltage across the source. So since it's not allowing us to go across the source itself, we could just go across both of them, and that's going to be the same as the total voltage of the source. So you see how it starts at 0? So what I'm going to do is draw this on my paper, what I am seeing. So this is the source voltage. It starts at 0. So the phase angle of the source voltage is 0. And then it goes up all the way to, what? Well, it's on a scale of 20 volts at the top, right? So we know the root mean square voltage across the resistor, 12.01. We know this one, we know this one, the current in the circuit, we know the period, and we drew the voltage of the source, 17, negative 17. Okay, now we could draw the voltage of the resistor and the voltage of the inductor. So voltage of the resistor would be just, this one goes across the resistor. Okay, so what is that equal to? It also starts at 0. Okay, then it goes all the way up to almost 17. So goes to 17, then comes back down 8.33, then basically negative 17. So it basically looks almost like the voltage of the source, but maybe a little bit smaller than it. So it kind of looks like this. This other one, the voltage of the resistor. So it pretty much resembles the voltage of the source. So if this top one is the voltage of the source, the voltage of the resistor is this smaller one, voltage of resistor. So it goes up with the source, comes back down, and goes like that. Okay. Then how about the voltage of the inductor, the other one? Then you're gonna go like this and like this. Ooh, way different, right? You see that? Way different. So at 0, it starts up almost at what's the voltage? Oh, notice that its scale is different. It goes from 0.5 volts to negative 0.5. So it starts almost equal to 0.5. Okay. So you see that? this is what the inductor voltage is showing on the oscilloscope. Like this, the resistor is like that, and the source is like that. So this one is the resistor. So let's see what the numbers are and how we can explain these. Okay, so let's calculate. The first thing to do is to calculate the capacitive reactance, which is 1 over WC, right? So 1 over 2 pi. Oh, actually, sorry. There's no capacitor in the circuit. The inductive reactance, omega L. And then omega is 2 pi FL. So what is my F is 60. My F is 20 times 10 to the minus 3. So remember, that's a measure of how much the inductor resists the circuit. So then that's 2 times pi times 60 times 20 times 10 to the power 3 negative. Oh, okay, so XL is going to be 7.54 ohms. Okay, and then the external resistor is 300. Okay, so the resistor of the source is 300. So now the total resistance of this circuit, so we expect the circuit to look like this, something, the Phasor diagram of the circuit. So we have the voltage of the current in the circuit will look something like this. The voltage of the resistor will be in phase with the current, and it will equal 300 times whatever the current is doing. So the current in the circuit and the resistor in the circuit are doing the same thing, they're in phase. So the current in the circuit should look like the second graph. You'll be in phase with that, but of course you'll be smaller than it by 300 times, right? Now the voltage of the inductor is going to equal whatever the current in the circuit times 7.54. So whatever the current, so imagine this is, let's see here. If the current in the circuit is like this small. So what was the sentence that we learned early? No, what was the thing that we learned? Oh, I didn't even teach you this. Eli the Iceman. Eli the Iceman. This sentence captures the phase difference. So this one says the voltage of the inductor is ahead of the current. Oh, we learned this a little minute ago, but we never said the sentence. Remember back here? Oh yeah, we wrote it down this way. The current in the circuit is behind the voltage of the inductor, right? And then here we wrote the current in the circuit is ahead of the voltage of the capacitor by pi over 2 radians. So if you take those statements, you can summarize it with this sentence, okay? You could say Eli the Iceman, so the voltage of the inductor is ahead of the current in the circuit, okay? And then the current in the circuit is ahead of the voltage of the capacitor. The current is ahead of the voltage of the capacitor, you see. So the way that the sentence works is that whatever comes first is ahead. So voltage of inductor is ahead of the current, and the current is ahead of the voltage of the capacitor. So in this case, whatever the current is doing, the voltage of the inductor will be ahead of that. So it will look like this. You see? So you see voltage of the inductor is ahead of the current. So then I put this voltage of inductor and I put it to the tip of this. It's like adding vectors. Voltage of inductor, and this gives me the total voltage of the circuit, the total voltage of the source. You see? So it's because the voltage of the resistor and the voltage of the inductor are not doing the same thing. So this gives you a vector summary of what this is showing in the oscilloscope. You see here how the voltage of the inductor is ahead of the voltage of the resistor. You see how it starts at its max already, and then so this one takes a little bit of more time to reach its max. So you see it's already at its max. Then it goes down to 0 and it reaches 0 before the resistor does. You see? Then it goes down to its minimum and it reaches its minimum before the source or the resistor does. You see? So you can kind of tell already by the oscilloscope that the inductor is ahead. The inductor is ahead. So cool. So the inductor is ahead of the voltage of the resistor, and this is the voltage of the inductor. So what's going to happen? This is R. The magnitude of this is XL. So then you have here R squared plus XL squared is the total impedance squared. So the total resistance of the circuit is going to be the magnitude of the hypotenuse of this. So square root of R squared plus XL squared. That's called the total impedance.
Professor, quick question?
Yes.
Where did the XL come from on the Phasor diagram again?
That's this one right here, XL 7.54. And it has to do with the magnitude. It's a measure of the magnitude of this. So for example, if you take the 300, the resistance of the resistor, and you divide it by this, 300 divided by 7.54, you get what? 300 divided by 7.54, around 39.63 times. So that means I'm expecting the voltage of the resistor, the peak voltage of the resistor, to be about 40 times larger than the peak voltage of the inductor, because the resistance of the resistor in that circuit is 40 times larger than the resistance of the inductor. Why? Because I'm at low frequencies. Inductors don't resist the circuit much when you're at low frequencies. You see? So now if I take the ratio of the peak here, which is almost 17 for the resistor, close to 17. Remember, the source voltage is 17. It peaks at 17. The resistor voltage is probably slightly smaller than the 17. And now the peak voltage of the inductor was, this might be around 0.4 something, right? So then take the ratio of those two. Where was I? Okay, so take the ratio of the resistor voltage to the inductor voltage. What is that? You see that? 42.5. So this is going to be similar to what you're going to be doing on the last lab. You're going to be proving all these things. So you see the peak voltage of the resistor should be around 40 times bigger than the peak voltage of the inductor. It just doesn't look that it's 40 times bigger the way the way that I have drawn. 17 should be much, much bigger, much higher like this. You see? So this circuit is being dominated completely by the resistor. It's almost as if the inductor isn't there. You see? Okay, so the impedance of the circuit is going to be what? 300 squared plus 7.54 squared. 300 squared plus 7.54 squared square root 2. Yeah, so the impedance of the circuit, 300.095 ohms. That's the impedance, which is just another way to say that's the total resistance in the circuit. Okay, so from here, I could already predict what the I in the circuit should read, the I root mean square in the circuit. It should read whatever the peak voltage was, the maximum voltage, divided by root 2, divided by the total impedance of the circuit. So this is I root mean square theoretical. So you take the maximum voltage, you divide by root 2, right? So what's my maximum voltage? 17 divided by root 2 divided by the impedance. So 17 divided by 2 root. Okay, that's 12.0208, right? So that's, I remember I'm kind of mimicking this as like our power outlets. And then divided by Z. Okay, so I'm expecting the current in the circuit to read that. And now what did it read? 0.040. So we don't know what the other digits were. That's the only thing that the multimeter gave us. Hey, we're close. Actually, we're right on. 0.040, you see. So then what would I expect each of the other ones to give me? The root mean square of the resistor. Right, then you just take this and multiply it by the resistance of the resistor. $12.017. Is that what it read? Aha, you see that? 12.01, right? And then the inductor read 0.302. So you see, all of them should check out. The inductor read. So then how do I get the inductor? You take the root mean square current, multiplied by XL, 7.54. You see, then what's going to happen? 0.04006, right, times 7.54, 0.302, 0.0524 volts. That's what it read. Yep, 0.302. So far, we're 0% error, 0.302. You see, it's pretty tough. So is that this graph is being added to the resistor graph, this smaller one, to produce this bigger one. And you might say, well, how is that happening? Because you've got two graphs that are out of phase from each other, and they're producing this guy. How is that literally happening? The mathematical way to do it, it would be to say, take every single time, and add this to that, and you get that. Add this to that, you get that. Add this to that, you get that, right? And then to add them literally to get this bigger graph, right? Oh. This is the vector way of analyzing what happens. As this is rotating like this is rotating, the source voltage is rotating, and then this is rotating, and their vertical components are telling you what each three of these are doing.
Okay.
Yeah. This is the general, the way that you would do it for in a math class. You know, you would take this value plus that value, you would get that. This and that, you get that, you get that. But because this graph is out of phase from this, it's not that easy to do. You know, so we've come up with this way to visualize it easier. So we could say, oh, okay, the net resistance acts as if it's the vector sum of these two.
Yeah, like I understand that, but I'm just confused as to why we can go straight to saying r squared plus xl squared is equal to z squared.
Yeah, very good questions, because you're trying to wrap your head conceptually around this concept, right? You see, in a DC voltage, if this is a DC circuit, you can say if this has a resistance of 300 ohms and this has a resistance of, let's say, 10 ohms, together they have a net resistance of 310. Because in a DC circuit, they will resist the circuit in phase with each other in the same way in a DC circuit. So there is no such thing as being out of phase. So their net resistance will be the sum of the two. But when this is an AC source, the instant that this resists the circuit most is when this resists the circuit least. You see, they're completely 90 degrees out of phase with each other. So when this guy is resisting at maximum possibility, this guy is not resisting at all. You see, that's what it means to say that the voltage of the resistor is 90 degrees out of phase from the voltage of the inductor. So it's kind of like two people that are resisting something. When this guy is, like, imagine two students in a class. When this guy is misbehaving, this guy is really behaving. And when this guy is misbehaving, this guy is behaving. So their net misbehaviorness is not the sum of their individual misbehaviorness, because they're out of phase.
Okay.
So in order to find their misbehaviorness, you do square root of this squared plus that squared.
Huh.
That's crazy. Huh. That's AC circuits right there.
All right. Thanks for watching.
Was just the Vm over root 2, right? 12.02. So they should have technically showed 12.02. I don't know why they showed 12.01. Because the magnitude of this, right, from here to here, should be slightly larger than the magnitude of this. Even if this is really small, but it should be slightly larger. So it's probably should say, when I do the whole thing, it should say 12.02. Yeah, it's not. They should round it up. The other thing we could check is the phase angle. What do I mean by that? That's this thing, the phase angle. How many radians is the source voltage ahead of the resistor? Okay, that's going to be hard to do experimentally because they're so close to each other, right? In other words, how much off is this from this? God, they're so close that it's going to be hard to calculate this. So literally you would have to go and see, okay, here's the source. You see where it is at 0, you see. And if you do the resistor, what should happen? The resistor should be slightly behind. Who should be behind? See, look here. The resistor should be slightly behind the source. Or you could say it the other way, the source should be slightly ahead. You see? So what does that mean? Well, the resistor should be crossing the origin slightly to the left. No, the resistor should be crossing the origin slightly to the right of when the source crossed it. But you see, it's so not noticeable. If you go like this, you see where when the source crosses the origin? Right there, right? Now blow that up. Now put it across the resistor. Do you see it's a little bit to the right? You see that, Daniel? Right there? It's crossing the origin a little time after the source voltage. That's the phase angle difference. But it's so small that it's hard to read it. You see that?
Right.
Now, how can I make that more noticeable? How can I make the circuit to where the circuit is not just dominated by the resistor, that the inductor has more say? If I make the inductor grow, then what's going to happen if I make the inductor grow, this is going to grow more. And then it's going to go like that. Then the source voltage is going to go like that. You see? And so now the source voltage will be much bigger than the resistor voltage. And they will share. In other words, it'll be more of a combination. So how can I make the inductor dominate more? Let's increase the frequency of operation by 10-fold. Make this 600 hertz. What's going to happen? XL is going to be 75.4. Right? So then if that's 75.4, what happens to your impedance? All the numbers change now. Everything, there's a trickle down effect. So the impedance 300 squared plus what? 75.4 squared. You see what happens? Just by changing the frequency by 10-fold. Now what happens to the Z value? It's still kind of dominated by the resistor, but not as much as before. 309.33. See, this became 75.4. So then now what's going to happen? The I root mean square changes slightly. It's a little bit less. The root mean square R is a little bit less, right? So this current is going to be less now. Okay, so then the new value is going to be 309.33, 12.0208 divided by 309.33. So the current is 0.03886 amps. Right? And then this guy becomes 0.03886. So this becomes a little bit less voltage of the resistor. You see the voltage of the source doesn't change. Voltage of the source, I'm keeping it 12.02. But the resistor voltage now gets a little bit less because the current is less, do you see? So the resistor voltage drops. 0.0388 times 300, 11.65. You see? But the source voltage is 12.02 still. But then what's the inductor voltage? 0.03886 times, well, now this is 75.4. You see that? 0.03886 times 75.4, 2.93. Well, now it's more noticeable. 2.93 volts. So let's check that, and then we can also check the phase angle. Okay, so change the frequency to 600. Just put the decimal right there. Ah, okay. Now take the multimeter, put it across the whole thing. Well, the whole thing shouldn't change because that's still the source. So 12.01 is still the source. Now put it across the resistor, 11.65. Is that what I got? Yeah, we got 11.658. You see that? This is the real way you can learn. Using this software is really, really good. Or there might be some online too, the free ones. Some free sites. Okay, then put it across the inductor. 2.93. See that? Then check the current. So go to AC current. What's the current? 0.039 amps. Is that what I got? Yeah, we got 0.03886. Yeah, so the current went down slightly, right? What else to check? So in terms of the multimeter, those are the only things to check. The total voltage, the resistor, the inductor, and the current. Then you can take that off. Now check the oscilloscope. Check the total voltage. Well, the total shouldn't change because, the only thing that should change is the period of change, that it's 3.33 milliseconds because the frequency I went up by a factor of 10. So that's the only thing that changes. It goes to 3.33 milliseconds. Okay, so that was that. Now, how about the inductor? Oh, you see that? It's it doesn't start at the top here. Let's see here. Okay, so now let's see here. Okay, so to really kind of get here the whole idea of when it starts and the phase angle, let's see here. How about the resistor? Oh, you see how it's off? You see now it's more noticeable. It crosses the origin slightly sometime after the source. So let's go to the paper. So this one is a lot more noticeable. So what should the phasor diagram look like? We got the current, we got the VR is 300 pi. Then we got XL is like this. BL. And this is V source. So the equation for V source is what? 17 sine of 2 pi 600 t. So the source is starting with a phase angle of 0, right? And it's the amplitude voltage is 17, and then it's 2 pi 600 t. So then let's calculate this phase angle. Tangent of phi is equal to XL, which is this is 79.4 I, right? I. So then it's XL over R. So this over this. So 79, was it 79? No, 75.4. 75.4 over 300. Okay, so now, go to radian mode. 75.4 divided by 300, then 10 inverse. So phi is 0.246 rads. So if I wanted to write down the equation for the current in the circuit, the current in the as a function of time, the current is going to be behind the source voltage. You see, behind the source voltage. So it's going to be 17 divided by my impedance. My impedance was what? 309.33. Right, so that's the new impedance that we calculated. So you divide the amplitude voltage by the impedance, then sine of 2 pi 600 t minus, because the current is behind the source voltage, minus 0.246 rads. Right, then the voltage of the resistor is in phase with the current, but just multiply it by 300. So then the voltage of the resistor as a function of time is 17 over 309 times 300 times sine of 2 pi 600 t minus 0.246. Okay. Then what's going to be the voltage of the inductor? The voltage of the inductor as a function of time is going to be the voltage of the resistor plus pi over 2. So whatever the resistor is, whatever the resistor or the current is, voltage of the inductor is ahead of them by pi over 2. So you add pi over 2 to that. Oh, then you multiply the current by XL, 75.4. So instead of multiplying the current by R, you're multiplying it by XL, which is this guy, right? 75.4. So 17 over 309.33, 75.4 sine of 2 pi 600 t minus 0.246 plus pi over 2. Okay, so now what is that equal to? Pi divided by 2 minus 0.246. 1.32479. So if I wanted to check these two, how much this is the phase angle, this is the phase angle of the current, the theoretical phase angle of the current should equal to the theoretical phase angle of the resistor, the voltage of the resistor, let's say, and that's negative 0.246. So what does that mean? The resistor should be behind the, it should be behind the source, right? The voltage of the inductor, let's see here. Yeah, the voltage of the inductor should be ahead of the voltage of the source. In other words, when you're doing here negative 0.246, you're starting at the source, you're going back to where the current is, then you're adding pi over 2. So this is this angle, that angle, as measured from the source. So it's 1.32479. So as measured from the source, the inductor is ahead by 1.32479. So take a look at when it's crossing the origin. See, this is one division. So I don't really necessarily care about how many seconds these are. I can just focus more on the number of divisions of this. You know, so this is 1 division, 2, 3, 4, 5. And they split 5 divisions to equal 3.33 milliseconds. No, actually not even 3.33, because it's from here 0 to all the way to here. That's actually 10 divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 10 divisions is equal to 3.33 milliseconds. So each division is 0.33 milliseconds. But I really don't care about the value of the division. All I care is that it takes about 0.2. Each of these is a 0.2. 0.2, 0.4, 0.6, 0.8. So it takes about 0.2 and a little bit more. 0.25 divisions, right? 0.2, maybe 0.2, 0.3. 0.3 would be here. 0.22 divisions. Do you see that? Slightly more than 0.2 divisions. So it takes 0.22 divisions longer for the resistor voltage to reach its 0 than the source voltage of the resistor is what? It's taking 0.22 divisions later for the resistor to reach its 0, and then you divide that by how many divisions are in one period of the motion, or in one period of the cycle, and that's 5 divisions, right? Then you multiply that by 2 pi rads. And you put a negative. Why? Because the resistor voltage is reaching its 0 after the source voltage. See, the source voltage looks like this, and the resistor voltage looks like that. See, always a little bit late to everything. So that means this phasor angle is correct. This is source. So the source is ahead of the resistor. You see? So then what would that be? That should be equal to this guy if we did it right. Okay, yeah. 0.276 radians. Maybe it was 0.21 divisions. I know it was a little bit more than 2. Really tell. Maybe it might be 0.21, slightly more than 0.2. If I had guessed 0.21, would that be better? So when you do this on the lab, you'll guess your best guess, and then you can say, can I change that slightly to make it even better? But I know it's a little bit more than 0.2. So then you say 0.21 divided by 5 times 2 times pi. Okay, that's as good as it's going to get. Okay, that's not bad. 0.264. Which is close. You see the right here? The inductor is reaching its 0 quite a lot earlier than the origin. You see? You see how the inductor is ahead of the source voltage? Right there. The source voltage crosses the 0 at the origin. You see? The inductor crosses the 0 when? How many divisions is that? This is 1 division, 0.2, 0.4, 0.6, 0.8. Is that 1? 1, 1.2. You see, this would be 1.2. So what is that? 1 is slightly right there. So maybe 1.02, something like that. 1.02, 1.03, because this would be 1.2. So let's say 1.03 divisions. So it's 1.03 divisions ahead of the source. You see, because it's ahead. So 1.02 divisions divided by 5 div times 2 pi rads. So you see the inductor source, the inductor looks like this. It's how it's quite a lot ahead of the source. Okay, so then that's going to be not bad. 1.2818 radians. See that? So if I had guessed maybe 1.03 divisions, that would have been even dead right on. Because I could tell it was slightly more than 1. Yeah, 1.29. Yeah, see 1.32 radians.